when multiple drones are working together in the same airspace, perhaps spraying pesticide over a field of corn, there is a risk they might crash into each other. To help avoid these costly crashes, MIT researchers presented a system called MADER in 2020. This multi-agent trajectory planner enables a group of drones to formulate optimal collision-free trajectories. Each agent broadcasts its trajectory so fellow drones know where it is planning to go. Agents then consider each other's trajectories when optimizing their own to ensure they don't collide. But when the team tested the system on real drones, they found that if a drone doesn't have up-to-date information on the trajectories of its partners, it might inadvertently select a path that results in a collision. The researchers revamped their system and are now rolling out Robust MADER, a multi-agent trajectory planner that generates collision-free trajectories even when communications between agents are delayed. The algorithm incorporates a delay check step, during which a drone waits a specific amount of time before it commits to a new optimized trajectory. If it receives additional trajectory information from fellow drones during the delay period, it might abandon its new trajectory and start the optimization process over again. When the researchers tested Robust MADER both in simulations and flight experiments with real drones, it achieved a 100% success rate at generating collision-free trajectories. While the drone's travel time was a bit slower than it would be with some other approaches, no other baselines could guarantee safety. MADER is an asynchronous, decentralized multi-agent trajectory planner. This means that each drone formulates its own trajectory and that while all agents must agree on each new trajectory, they don't need to agree at the same time. This makes MADER more scalable than other approaches, since it would be very difficult for thousands of drones to agree on a trajectory simultaneously. Due to its decentralized nature, the system would also work better in real-world environments where drones may fly far from a central computer. With MADER, each drone optimizes a new trajectory using an algorithm that incorporates the trajectories it has received from other agents. By continually optimizing and broadcasting their new trajectories, the drones avoid collisions. But perhaps one agent shared its new trajectory several seconds ago, but a fellow agent didn't receive it right away because the communication was delayed. In real-world environments, signals are often delayed by interference from other devices or environmental factors like stormy weather. Due to this unavoidable delay, a drone might inadvertently commit to a new trajectory that sets it on a collision course. Robust MADER prevents such collisions because each agent has two trajectories available. It keeps one trajectory that it knows is safe, which it has already checked for potential collisions. While following that original trajectory, the drone optimizes a new trajectory but does not commit to the new trajectory until it completes a delay check step. During the delay check period, the drone spends a fixed amount of time repeatedly checking for communications from other agents to see if its new trajectory is safe. If it detects a potential collision, it abandons the new trajectory and starts the optimization process over again. The length of the delay check period depends on the distance between agents and environmental factors that could hamper communications. If the agents are many miles apart, for instance, then the delay check period would need to be longer. The researchers tested their new approach by running hundreds of simulations in which they artificially introduced communication delays. In each simulation, Robust MADER was 100% successful at generating collision-free trajectories, while all the baselines caused crashes. The researchers also built 6 drones and 2 aerial obstacles and tested Robust MADER in a multi-agent flight environment. They found that while using the original version of MADER in this environment would have resulted in 7 collisions, Robust MADER did not cause a single crash in any of the hardware experiments. Drones were able to fly 3.4 meters per second with Robust MADER, although they had a slightly longer average travel time than some baselines. But no other method was perfectly collision-free in every experiment. In the future, the researchers want to put Robust MADER to the test outdoors, where many obstacles and types of noise can affect communications. They also want to outfit drones with visual sensors so they can detect other agents or obstacles, predict their movements, and include that information in trajectory optimizations.